What's up, kids? This is physics class, and I'm Brock Bishop.
I'm Matt Seller.
And I'm Ben Kendall.
Today, we're going to be talking about fluids. In specific, I'm going to be talking about fluid flow.
I got Archimedes' principle.
And I'm going to talk about the calculations of both of those experiments.
This is going to be a fun video, and I hope you enjoy it. Cheers.
Go Bucks.
The exploratory lab fluids had two experiments within the lab itself. The first experiment, which I will be talking about right now, is entitled Fluid Flow, and the second one is entitled Archimedes' Principle, which will be talked about later on in the video. To introduce the experiment Fluid Flow, we need to realize that fluids have tendencies within a container. When you pour water into a water bottle, the water obviously takes the shape of the water bottle itself. Much like this, a fluid will take the shape of its container. Water is a liquid, and a liquid will form a surface as gravity pulls it to the bottom of the container. When dealing with pressure and velocity, we need to realize that this fluid's tendency to conform to its container is going to affect the pressure and velocity. So throughout this experiment, we're gonna measure and try to find differences in the pressure and the velocity itself, and see how they can relate to the size of the container. So the objectives of the fluid flow experiment are going to be to observe the effects of fluid flow itself, to measure the pressure drops of fluid flowing through restricted channels of the Venturi apparatus, and to understand the Bernoulli effect, which is basically when a fluid flows within a channel, the pressure may drop as the flow velocity increases. So understanding these objectives will be important as we understand the experiment itself. When dealing with this fluid flow experiment itself, a couple practical applications that just popped in my head were when you when you put a water balloon to a hose and you fill that water balloon up, we see the fluid going from an area of higher pressure in the hose to an area of lower pressure when it gets shot into the water balloon. Another similar practical application would be a fire hydrant. When firemen need to hook up their hose to a fire hydrant, they put it to the fire hydrant. The fire hydrant releases the water into the hose, and it goes from the hose obviously out into the air where the pressure is completely released. So these two practical applications kind of give us a good real life example of how fluid flow works. The basic idea of the fluid flow experiment itself is this. We have a water reservoir, which is right here, obviously containing a substantial amount of water. And from that reservoir, we have a tube that is running and connected to the Venturi apparatus, which is more clearly seen over here. On that Venturi apparatus, there's 4 small tubes connected to the quad pressure sensor that gives us a way to sense the pressure at 4 different points on the Venturi apparatus. From that Venturi apparatus, we have another little tube running off of it, and that tube is in a bucket at the very end, which is where all the water goes into once it's done flowing.
Let's watch.
Taking a closer look at the water reservoir, we see a motion sensor hanging right above it. The purpose of this motion sensor is it records the position of the water surface as a function of time. So we can also calculate the cross-sectional area of the cylinder from a measurement of its diameter, and we combine this cross-sectional area with the velocity of the water surface, which allows us to find the volume flow rate.
Science, science, science!
Looking now at the quad pressure sensor and the Venturi apparatus, we see 2 pretty good pictures of them. First, we have a clear plastic seal with 8 bolt holes right here. Here's the 8 bolt holes, these 8 things right here, and there's that clear plastic seal, obviously to keep the water in. And then we have the 4 tubes that run to the quad pressure sensor right here. And then we have the pressure at each of these 4 points, which are point 1, point 2, point 3, and point 4. So we obviously know that the gravity feeds the water through the apparatus at an approximate constant volume flow rate, and the quad pressure sensor measures this absolute pressure at various points within the Venturi apparatus, which are these 4 points right here. So the Venturi apparatus and the quad pressure sensor are obviously vital to this experiment as we get a very detailed look at the pressure at each of these 4 points. Finally, we have the clamp and the container. On the tube running off of the Venturi apparatus that went into the container, we had 2 clamps on it. We had one clamp that was positioned nearest the Venturi apparatus, and then we had clamp 2, which was positioned towards the end of the tube, like close to the container area. For the fluid flow experiment, we made sure it asked us to have clamp 1 open during every test run, completely open. So we had clamp 1 completely open throughout the experiments, and then clamp 2 varied a bit. Our first experiment, we had clamp 2 completely open, and we did many test runs with clamp 2 completely open to just to get a average, just to get some good testing. Then we moved on and we closed clamp 2 by 1 click, so it was still open, but as you can kind of see in this, it was like partially opened. And we did many test runs with clamp 2 closed by 1 click. Finally, we had clamp 2 closed by 2 clicks, and again we ran it numerous times to get averages and to get some solid results. So obviously the data will vary between clamp 2 being open, clamp 2 being closed by 1 click, and clamp 2 being closed by 2 clicks.
And now it's time for data! For the fluid flow experiment, we found the area of the skinny part of the apparatus and the thick part. We called the skinny part A1 and the thick part A2. During the experiment, we used Pasco tools to record the change in depth of the water in the graduated cylinder. Science rules! Using these areas and the change in depth, we calculated the velocity of the water in the other areas. We measured the pressure before the flow started and called it the baseline pressure. We also took pressure measurements while the water was flowing. We used the baseline pressure combined with the measured pressure to find the actual water pressure. Finally, we found the difference between our measurements and what we would theoretically expect the pressure to be based on calculations. This difference could be caused by turbulence, friction, or a combination of the two. All of these measurements were taken first with the clamp completely open, then with the clamp closed 1 click, and finally with the clamp closed 2 clicks. After we had done all of these measurements for each of the 3 times we ran through the experiments, we averaged all of the results. We also found the percent difference between the measured pressure and the calculated pressure. In all cases, this difference was less than 0.25%.
In our experiments, we also tested Archimedes' principle. To test the effects of depth and pressure on an object, we submerged a water pressure apparatus, which is a cylinder that has membranes on either end, into a tank of water. First, we oriented the cylinder so that the membranes were on a horizontal plane. As the cylinder was lowered into the tank, it became more and more difficult and required more and more force to push the cylinder downward. We observed that as the cylinder was lowered deeper into the tank, the membranes on either side seemed to be pulled or pushed inward. It also looked as if the membranes were pushed the same distance into the cylinder. We removed the cylinder from the water and oriented it so that the membranes were above and below one another. Again, we submerged the cylinder into the water. However, we saw something different this time. It seemed small, but the bottom membrane was being pushed slightly farther into the cylinder than the top. The reason for this made sense after we learned more about Archimedes' principle. We also tested Archimedes' principle to see if the buoyant force affected the weight of a submerged object. We started by weighing a brass valve on the scale. Then we tied a string around the valve and hung it from the scale and submerged the valve completely underwater. Then compared the weights. The weight of the valve to begin with was 174.6 grams, while the weight of the valve when it was submerged was 153.5 grams. We then tested a solid copper cylinder to make sure that the weight results were consistent, and they were. Archimedes' principle says that the buoyant force is equal to the weight of a displaced fluid. The buoyant force is the net force that is exerted on an object that is immersed in a fluid. The weight of the displaced fluid is the density of the fluid times the volume of the displaced fluid times the acceleration due to gravity. In other words, if an object weighs less than the weight of the water that it displaces, the object will float. If it weighs more, then the object will sink. We concluded that this buoyant force was the resistance that we felt as we tried to lower the cylinder deeper and deeper into the tank. Archimedes' principle also states that as the depth of the object increases, the pressure that is exerted on the object also increases. This would explain why the membranes on the cylinder were forced inward as it was lowered into the tank. This also explains why when the membranes were placed on top of one another, the bottom membrane was forced farther into the cylinder than the upper membrane. In addition, our experiments with the pressure apparatus were consistent with Archimedes' predictions, meaning that as the cylinder was lowered deeper and deeper into the tank, the pressure exerted on it became greater and greater. After conducting our experiments, making observations, and analyzing our data, our group concluded that our results were consistent with Archimedes' principle, showing it to be true.
Apparent weight data.
We used mass and volume to calculate the density of each object. We then weighed each object suspended in the air and suspended in water. After we had done this, we calculated what the apparent weight should be using the densities found earlier plugged into the formulas from the Archimedes principle. Finally, we found the percent differences between the calculated apparent weight and the measured apparent weight. For the copper cylinder, the difference was very small, less than 0.03%. For the irregularly shaped brass object, the difference was a much larger 2.64%. This indicates that there may have been some measurement or procedural errors during the experiment.
Well, thank you guys for watching the video. We hope you enjoyed it. Again, this is Brock.
This is Matt.
And I'm Ben.
Stay safe, stay in school, you stay classy, PHY 2014-1.